Hello everybody. So welcome to this lecture number 2 of week 11 on the course on linear systems theory. As we saw in the previous lecture, we redefined our control problem in terms of certain optimality conditions to be fulfilled, and then we had a couple of methods to derive conditions for what we call as LQR controller, which essentially ended up in solutions or in the form of some kind of a equation called a Ricatti equation. So today we will look at one more method to derive that particular equation, and also we will look at what to do with the Ricatti equation, when does there exist solutions if at all, and how do we derive those conditions for existence of solutions of Ricatti equations. Okay, so to begin with, so this method will be based on what is called as feedback invariants, and will closely relate to what we had done also in the previous lecture, and why well, both methods are kind of similar. Okay, so the first thing here is to look at the following. So if I have a system, again I'll just look at a standard LTI system, a functional H defined on x and u is a feedback invariant for the LTI system if, when compared or when computed along a solution to the system, its value depends only on the initial condition and not on the specific input signal u. For example, for every symmetric matrix P, this particular functional is a feedback invariant for the LTI system as long as the system is stable or asymptotically stable, or in other words limit x tends to infinity, limit t tends to infinity, x of t goes to 0. Okay, so we will do a little proof of this, right. So what we have to show is we are given a function of this form, h on x and u is integral with a negative sign 0 to infinity a x of t plus b u of t p x of t plus, so this is the transpose, right. So x transpose of t p a x of t plus b u of t with a dt. Okay, so this thing inside the integral is nothing but integral from 0 to infinity of x dot transpose p x dt, right. So and this integral looks takes some very nice form here. So x of 0 p x of 0 minus limit x going to infinity x of t p x of t, and the system is stable. This will go to 0 as t goes to infinity, and what I am left with is just this one, p x of 0. Okay, so this functional therefore is a feedback invariant, right. So what was the definition is that its value depends only on x at 0 and not on the specific input signal u. So if you remember in the lecture number 1, we had used something very similar here, right. So this exactly was what we derived. So now we give it a little formal notion in terms of feedback invariance, right. So nothing really new happening here, but we are just trying to give it some more general or give it a little more systematic meaning, right. Okay, so now how do we derive the optimal control law from here? Okay, so suppose we are able to express the cost function to be minimized by a certain u in this form, right. So j is the cost function to be minimized, h here is a feedback invariant, and this term in the integral is such that it has so that the minimum is 0, right. The control u of t, this minimizes j, whose optimal value is equal to the feedback invariant. Okay, so we will just read it out again. So I suppose I am able to express my cost function right, to be minimized in this form, right. So, the previously defined cost functions could easily be written in this form, and we will see shortly why that is true, right, where the first term is a feedback invariant and the second term, this integral, is such that for every x belonging to n, the minimum is 0. In that case, the control u of t, which is the argmin, which is the u that minimizes this to 0, and this u also minimizes j, whose optimal value is equal to the feedback invariant. And we will revisit this statement once we derive what this means here. Okay. So, we start with a little more general form of quadratic function. We just add in addition to what we had previously, just some cross terms between x and u. Okay. So, the theorem that we will prove, again will derive the same Ricatti equation, but in a slightly different way. So, we assume that there exists a symmetric solution to the below Ricatti equation, for which this particular thing is a stability matrix. The feedback control law u equal to minus kx, which with this k, so this u minimizes the LQR criterion 1 and leads to j LQR of this form. Okay, very similar to what was here, right. This was the j LQR which we had derived, and we will just derive it from a slightly different point of view. Okay. So, let's do quickly the proof of this, and it will turn out that it's not really difficult to understand or even interpret. Okay. So, the objective again is to minimize the cost function. So, I have j LQR is 0 to infinity. So, this is already given, right, x transpose qx u transpose r u plus twice x transpose n u dt. Okay. Now, can I so the first step would be to just check if I can write it in this way, if I can write the j as something like this, right, where h is a feedback invariant and something inside the integral which eventually goes to 0, and the u that makes it 0 will be my optimal u. So, we will start from that. Okay. So, before that, let us again revisit this this result. So, from this result what we can see is that I can just take this to the left hand side, and I can write this as h plus the term in the integral is equal to 0. So, I will just exploit this relation and use it for the proof. So, this j LQR now can be written as in the following way. So, I have h x u plus integral 0 to infinity x transpose qx plus u transpose r u plus twice x transpose n u plus a x plus b u transpose p x here plus x transpose p again with the close a x plus b u, right, all with dt. So, this additional term just come from here. Okay. So, I just rearrange terms. So, I have h x u plus integral 0 to infinity x transpose. So, I have a transpose p plus p a plus q plus u transpose r u plus twice u transpose b transpose p plus n transpose x, everything with dt. Okay. So, let me first see what this quantity looks like. U plus kx r with the transpose here, u plus kx with k as r inverse b transpose p plus n transpose. This comes from the theorem statement here, this one. here. Right. Okay. So this will expand to the following. So I have U transpose R U plus X transpose P B plus N R inverse B transpose P plus N transpose X plus twice U transpose B transpose P plus N transpose times X. Okay. So I will write these two terms here, which correspond to the term here and here, in terms of this quadratic function here and this term corresponding to this x transpose and x. Okay. So and then substitute for this value of k. So the JLQR will now take the following form. So I have H x U plus integral 0 to infinity x transpose. So all these things will come as it is, A transpose P plus P A plus Q minus, because it just goes this side, right. So minus P B plus N R inverse B transpose P plus N transpose X plus this term here, U plus Kx transpose R U plus Kx. Okay. Now look at the term inside here, right. This term, okay. So all this will be under the integral. So all this will be under the integral dt. Look at this term carefully, and then also this term, right. So first let us check this, right. So if I put this to 0, which means A transpose P plus P A plus Q minus P B plus N R inverse B transpose P plus N equal to 0, right. So if I put this to 0, how can I put this to 0? Well, A is given to me, I know what is Q is given to me, B is given to me, R, also N, everything is given to me except P, right. So if I can find a P, if one can find a P which sets this term inside the bracket here to 0, okay. So what is my eventual aim? My eventual aim is to set this term inside the integral to 0, okay. So the first question is, well, can I find a P which sets this to 0? Okay. If the answer is yes, then what else is remaining? The other term that is remaining here is okay. So sorry, this entire thing will be in dt. The other term that is remaining in the integral is this guy, U plus Kx transpose R U plus Kx. And I ask the question, when does this have a minimum? Okay. So it is a straightforward answer, right? This will have a minimum when, okay, let's write down it more systematically. So this term U transpose R U plus K times X will have a minimum when precisely U equal to minus Kx with K given as R inverse B transpose P plus N transpose, in such a way that the closed loop system now, which is x dot, is A x plus B U, with U equal to this minus Kx is A minus B R inverse B transpose P plus N transpose X. Okay, so that this is a stability matrix. Okay. So now Let us go back. The u, which is equal to minus kx with k being of this form, this we show that this minimizes this JLQR, okay, and for which this closed loop system is now a stability matrix. That is pretty neat, I would say, to show. Right. So this was another way of looking at the Ricatti equation. Now, what we need to show is well, do solutions exist, or a bunch of questions we need to answer once I have derived the theorems, like there is a p which does blah blah blah, then u equal to minus kx minimizes a certain function and so on, right. Okay. So, what are the questions to be asked, right. The first is, under what conditions does the LQR problem have a solution? Okay. Now, similarly, under what conditions does there exist a p, or we go back to this slide, under what conditions does there exist okay, it should be A transpose p, does there exist a p which, so under what conditions does the ARE or the algebraic Ricatti equation have a symmetric solution, which is precisely to do with the existence of p that leads to an asymptotically stable system, right. The closed loop system must be stable. Okay. Now, does it also always mean that if I can find a solution to the LQR problem, it also, does it also always mean that the solution to the that one can find the solution to the LQR problem by only solving for the algebraic Ricatti equation? So, if I can find a p, does it also mean that I have solved the LQR problem? Okay. And lastly, a question that we will also ask is, does the Ricatti equation by itself provide any guarantees for the closed loop system? Okay. So, these are the questions that we will try to answer. Okay. So, first the first step to here to analyze this problem regarding the solution of the Ricatti equation is to determine or to define something called the Hamiltonian matrix. Okay. So, what does it mean when I say I am looking at the solution to the LQR problem? Well, the solution to the LQR problem, it requires existence of the solution p to this equation, right. Everything else apart from p in this equation is given, and such that this closed loop system is, or the closed loop A matrix is indeed a stability matrix. Okay. So, I just rearrange terms a little bit and say that this ARE, the algebraic Ricatti equation, can equivalently be written in this form. So, P identity with a negative H and IP, and this H will takes this form. So, I will skip the details, but you can just derive this for yourself. Okay. So, first definition here is that this matrix H is called the Hamiltonian matrix associated with this algebraic Ricatti equation. Okay. Now, what is the good thing about this? Okay. So, the first thing that we will further define is that a Hamiltonian matrix H is said to be in the domain of the Ricatti operator if there exists a square matrix H and a square matrix P such that this relation holds. H times M, where M is just identity, and P equal to M times Hs, with this Hs being a stability matrix. Okay. So, the first thing, okay, what does it mean by this Hamiltonian matrix being in the domain of the Ricatti operator? Okay. If something like this holds, where H is a stability matrix, then, well, P satisfies the algebraic Ricatti equation, right, the P here, and then we will slowly see how to derive this P also. If I can write a structure of this form, Hm equal to M Hs, this expression actually means that the matrix H is in the domain of the Ricatti operator, okay, with an M which takes this form, P is a square matrix, then this P which exists here satisfies the ARE. We will find later what this P precisely is. Second, this Hs here is precisely equal to the closed loop matrix that we derived here, this one, A minus BR P transpose and so on. Okay. this is a stability matrix, and towards the end that P is also a stability matrix. Okay. So let's spend some time deriving that. Okay. The first thing is, okay, so H time M is M times Hs with M of the following form I and a P. Okay, so first is we must prove that P satisfies the A R E. P satisfying the A R E, we wrote down it in terms of the Hamiltonian matrix in this form: P with a minus I, the H I P equal to 0. This is my A R E, right, in terms of the Hamiltonian. Okay, perfect. So just to prove, what was the first statement to prove? That this P which comes from here, that this actually satisfies the A R E. Okay, so take this expression again here, H M, okay, and then left multiply this with P and minus I. Okay, on the right hand side I will still do the same. I have P minus I M H S. Okay, so what does this mean? This is P minus I, on the left hand side H, my M is of the form I and P. On the right hand side I have P minus I, M is of the form I and P, and here I will have Hs, and this is equal to 0, right. So this here and this are the same, right, and therefore this P satisfies the Ricatti equation. Okay. Now what was statement number 2? Statement number 2 was to show that this Hs is precisely the closed loop matrix. Okay. So how does H look like? Okay, let me just write down how H looks like again. This is A minus B R inverse N transpose minus B R inverse B transpose minus Q plus N R inverse N prime minus A minus B R inverse N prime. Okay. So this is how the H looks like. Okay. Now substitute this H, okay, into this equation. Okay. So this H, let me just put it in this H. M is M times Hs. Okay. Now what is my M of the form? M is of the form I times P. Okay. This is equal to I with P and Hs, not I times P, just I and P. Okay. Now I am just only interested now in this, the first row, right. So this is A minus B R inverse N transpose minus B R inverse B transpose P is I times Hs or equal to Hs. So this I can rewrite again as A minus B R inverse. Okay. So I have terms say B transpose P plus N inverse, sorry, N transpose is Hs. This is exactly what was in the theorem statement, this one, right. Therefore Hs precisely takes this form. Okay. So the last step is to show that P is symmetric. Okay. So I again make use start from this expression, it is H times M is M Hs, okay. This M is again I and P. Okay. Again I left multiply this by minus P I H I and a P, this is minus P transpose I P Hs. I just pre-multiply both sides by this term, and here this will look like the following. This is P minus P transpose times Hs. Okay, so this can be shown to be symmetric from the definition of H. Okay, I'll just leave that that as for you to prove. Very straightforward process. Okay, so if the left hand side is symmetric, the right hand side should also be symmetric, which means P minus P transpose Hs is Hs transpose P transpose minus P. This is also equal to minus Hs transpose P minus P transpose. So, which means that P minus P transpose Hs plus Hs transpose P minus P transpose is equal to 0. Okay. Now, I just multiply this expression in the left by this term, on the right hand side I will multiply this by this, similarly here on the left hand side by this and the right hand side by this, and this will precisely turn out to be the following, that d over dt of e power Hs transpose t P minus P transpose e power Hs t is equal to 0. Similar proofs that we also did while we were proving stability, right. Okay, so we'll still use the same concepts here. Okay. Now, what does this tell me? That d by dt of this term is 0, that this term inside is a constant. Okay. Now, what do we know? We know that Hs is a stability matrix. If Hs is a stability matrix, this term will go to 0 as t goes to infinity. Okay. And therefore, so this function is in this way, right, is something like this, constant. Okay. So, whatever is the value at infinity should also be the value at 0, right. So, therefore, the value of this function should be 0 for all t. So, you have that e power Hs P minus P transpose e power Hs t equal to 0, okay, because at infinity it is 0, it should also be 0 over here. Now, this is invertible, e power h. So, the only option left is for P to be symmetric. Okay. So, we have proved the following, right. So, if H is in the domain of the Ricatti operator, right, which means an expression like this holds, then P satisfies the algebraic Ricatti equation. This Hs is precisely equal to the closed loop stability matrix, and P is also a symmetric matrix. Okay. Now, the next thing would be, okay, how do we find this P? Are there ways to, so what do I know, what is the information that I have? I have H. So, given this H of this form, can I find out a P? Now, look, look at closely, right. All the terms in H are known to me. A comes from the system matrix, B comes from the system matrices, Q, R and N all come from the from my cost function. Okay. So, given this H, can I now find a P, okay, making use of the expression that we have here. Okay. So, let us define something quickly. So, given a square matrix M, we can always factor its characteristic polynomial as a product of polynomials with roots having a negative real part and a positive real part. I will call them the stable and unstable, or just S and U. Okay. Something that is easily observed is that the stable subspace of M is just the kernel of delta S of M. Okay. So, this is also easy. So, what is easy to check here is that the dimension of this is also the degree of delta S of S, okay, or the stable subspace. Now, in addition, for every matrix V whose columns form a basis for Vs, the stable subspace, there exists a stability matrix Ms whose characteristic polynomial delta S is such that this relation holds. Something similar to the controllable decomposition kind of thing that we did. Okay. Now, okay, what does this mean? That the dimension of Vs, right, so which comes from here, or the stable subspace of M, is equal to the number of eigenvalues of M with negative real parts. Okay. It is just in general, right. I do not know what is the matrix M, I just know it is a square matrix, and I can factor its characteristic polynomial as a product of polynomials which has roots on the left half plane, which has roots on the right half plane, and so on, and I can say that the dimension of Vs is equal to the number of eigenvalues of M with a negative real part. Okay. So, now what we need to find here is find conditions under which the Hamiltonian matrix H belongs to the domain of the Ricatti operator, that is existence of matrix H such that this holds, right. So, we want to find when can I find a solution and how does the solution looks like. So, such a matrix H S exists if we can find a stable subspace of Hs, it should be not Hs, stable subspace of H of the form something like this, right. So, it was here, right, this one, I need to find something like this, right. So, what did I prove here is if I can find something like this, then this relation holds. Now, I will ask a question, when can I find some relation like this. Okay. So, now first is this is possible, and we will see that shortly, is this is possible when the dimension of the subspace is dimension of the stable subspace is precisely equal to n. Okay. So, let us see how that looks like, some small computations will show that. So, I need to find, or what is the dimension of the stable subspace of H. Okay. So, let us do something. So, to take H, multiply it 0, a skew symmetric matrix. So, this will give me B R inverse B transpose A minus B R inverse N transpose A minus B R inverse N transpose the whole transpose minus Q plus N R inverse N transpose. This is also equal to 0 minus I 0 with H transpose. Okay. If I call this J, what I have is H times j is j times h. Okay. The j is invertible, therefore, h is it should be a minus here. Okay. So, h is minus j h j inverse. Okay. Now, let us see what can we infer from this. Now, what do I know is that the characteristic equation is invariant under similarity transformations. Okay. Now, see, so the characteristic equation of h is the determinant of Si minus h is equal to the determinant of Si plus h is now can be written in this way, right, j h j inverse, okay, with okay, something is wrong here. Should be a h transpose here and a h transpose here and here. Okay. This is also equal to the determinant of Si plus h transpose S, because the characteristic equation is invariant to similarity transformation plus also matrix transposition. That A and A transpose will have the same characteristic equation. Okay. Now, this is equal to determinant of Si plus h. Okay. This is also equal to now minus 1 power 2 n determinant, or if I replace the s with a minus, determinant of minus s times I minus h. This is equal to delta of minus s. Okay. So, delta of s was equal to delta of minus s, which shows, okay, what does this mean, right. So, this and this means that if some lambda is an eigenvalue of h, then minus lambda is also an eigenvalue. Right. So, this is and moreover it is of the same multiplicity. Okay. And therefore, if n h as, so h was what, it was from R to n cross 2 n. So, if there are n eigenvalues here, there will be n eigenvalues here also. Okay. Now, this will be possible only if there are no eigenvalues on the imaginary axis. Okay. Now, so if this condition is satisfied, that there are no eigenvalues on the imaginary axis, then H, the Hamiltonian matrix, will have n eigenvalues here and n eigenvalues here, which means that the dimension of the stable subspace of H is equal to n. Okay. Now, how do we ensure that there are no eigenvalues on the imaginary axis? Okay. So, the next result will prove that. So, we assume that if Q, if this is greater than 0, moreover, if the pair AB is stabilizable and this pair is detectable, then the Hamiltonian matrix has no eigenvalues on the imaginary axis, and therefore, this is obvious that the dimension of its stable subspace is n. Okay. So, let us quickly do that. Okay. So, as usual, we prove by contradiction. Okay. So, let x be x1 transpose x2 transpose be an eigenvector of H associated with eigenvalue j omega. Okay, so actually prove actually assume, okay, this will belong to some complex numbers C. So this x1 and x2 will both be in the set of Cn. Okay, so assume that let me assume that there is some eigenvalues which are sitting here. Okay, and see what happens to the assumptions that we made, or to the problems that we are dealing with. Okay, this means that okay, if I go back to my Hamiltonian matrix, this means that j omega I minus A plus B R inverse N transpose B R inverse B transpose Q minus N R inverse N transpose, and finally j omega plus A minus B R inverse N transpose full transpose with x1 x2 is actually equal to 0. Okay, now if again lambda and x are eigenvalue eigenvector pairs of H, right, and H is real valued, okay, so I can rewrite this as x1 star x2 star H x1 x2 plus x1 star x2 star H transpose x1 x2. This I can rewrite as x okay, set x2 star x1 star x1 x2 plus x1 stars will be x2 x1. Okay, the transposition and all, it takes this form, and the stars denote the complex conjugate. Okay, so okay, I'll skip the steps, but this is easy to check that this will equate to 0. Okay, so what does this mean? That if I take the left hand side of this expression, that this entire thing will equate to 0, I have the following. I have x2 star x1 star A minus B R inverse N prime minus B R inverse B prime minus Q plus N R inverse N prime minus A, sorry, minus A minus B R inverse N prime the whole prime x1 x2 plus again x1 star x2 star. So, I will have entire H transpose x2 x1 is this is equal to twice x1 star Q minus N R inverse N transpose x1 minus, sorry, minus twice x2 star B R inverse B transpose x2. Okay. Now, this is equal to 0, right. If this is equal to 0, what do we conclude? If this should be equal to 0, Q minus N R inverse x1 equal to 0, okay, and also B prime x2 should be equal to 0. Okay, we know that R inverse is that R inverse is always greater than 0. Okay, and therefore, the only possibilities are these two, 1 and 2. Okay, now this expression combined with this gives me a couple of additional conditions, which are that j omega I minus A plus B R inverse x1 equal to 0. Not only that, in addition I have j omega plus x2 equal to 0. Okay, now let us see what each of these statements mean. Okay, first is there is an eigenvector, and what is this eigenvector? This eigenvector x2 of A prime in kernel of B prime, this plus this, which means A comma B is not stabilizable. Okay. Moreover, then there is an eigenvector x1 of, from these two expressions, of Q minus N R inverse N prime, eigenvector of not this one, eigenvector of A minus B R inverse N prime in kernel of this thing Q minus N R inverse N prime, from these two expressions, these two. First one was these two, the second one was these two. This means that the pair A minus B R inverse N prime Q minus N R inverse N prime is not detectable. Okay. Now, let us go back to the theorem statement. When A B is stabilizable and this pair is detectable, then these things happen. Okay. Now, when I assume that there are eigenvalues on the imaginary axis, these two conditions are violated, and therefore, the Hamiltonian matrix H has no eigenvalues on the imaginary axis, and therefore, the dimension of its stable subspace is n. One step we have proceeded further. Right. Okay. Now, how do I find the basis for the stable subspace of H? So, my eventual idea is to find how this P looks like. Okay. Okay. So, let us now I know that the dimension of Vs is n, the stable subspace of H is n. Okay. Now, let me just take some arbitrary basis, right, like let V which is V1, V2 be a matrix whose n columns form a basis for the stable subspace of H. Okay. Now, assuming that V1 is non-singular, I can write V times V1 inverse in the following way, right, I and P, where P is V2 V1 inverse. Now, if V is a basis, then V inverse is also a basis for Vs. Okay. And therefore, we conclude that from where do we how what is the property that we will exploit now? we will exploit this property here, the property of stable subspaces. For every matrix V whose columns form a basis for Vs here, right, sorry, for every whose columns form a basis for the stable subspace, right, there exists a stability matrix, this one, whose characteristic polynomial delta S is such that MV is VMS. Okay, I am just writing the same. There exists a stability matrix Hs such that H times IP, this is my V, right, is IP times Hs. Okay. Now, this also implies now that H belongs to the domain of the Ricatti operator. That was from the definition, right. The definition of the Ricatti operator, H is said to be in the domain of the Ricatti operator if there exist square matrices such that this holds. Okay. Now, this, so what did we do? We just use the properties of stable subspaces, one. Second is that the nature of the Hamiltonian matrix H is such that it has n eigenvalues with negative real parts, n eigenvalues with positive real parts, which means that it has a stable subspace of dimension n, right. Now, we construct the basis for the stable subspace in this way and show that there exists a stability matrix such that this holds, and therefore, this H belongs to the domain of the Ricatti operator. Now, once H belongs to the domain of Ricatti operator, I know a bunch of things, right, that P satisfies the Ricatti equation, Hs is a stable matrix, P is symmetric, and so on. Okay. Now, we can now sum up all the results into the following, results from all the theorems and lemmas, that assuming that this matrix is greater than 0, stability of AB and detectability of the pair of this pair, then H is in the domain of the Ricatti operator, P is symmetric and it satisfies the algebraic Ricatti equation, this we already proved, right, and then the eigenvectors of H, eigenvalues of Hs are the eigenvalues of H with a negative real part. Okay. Now, I know under what conditions does P exist, and I also know what P looks like, right. So, P looks like that I can just find from here, right, and all depends on identifying the stable subspace of H and saying that all its eigenvalues are equally distributed in the negative and the positive axis, and nothing, no eigenvalues exist on the imaginary axis. Okay. Now, okay, we will do a little some examples, maybe I will have a separate lecture on some of these, on some problems related to this. Okay. So, that kind of concludes the main topics that I wanted to cover in week 11. In next week we will really find out, okay, what are the computational issues now associated with finding these P's. Can we write those as linear matrix inequality, starting from the solution to the Lyapunov equation till the Ricatti equation, and few other problems that in general control literature encounters. So, some computational tools in the form of linear matrix inequalities is what we will do in week number 12. It is usually not covered in many of the standard textbook courses or any other courses on linear systems, but okay, since this is one of the first advanced level courses that we are doing on NPTEL. We would like to really even give you a little exposition to some other areas that you can reach out to from this. Just a little introduction to few other topics also as a result of this course. So that's coming up next week. Thanks for listening.